So let's go ahead and get started. So chapter 7 is on carbohydrates. What are carbohydrates? What's an example of a carbohydrate? What's an example of a carbohydrate?
Glucose.
Cellulose, glucose. Yep. So what makes up a carbohydrate?
Monosaccharides.
Well, I mean, what elements make up a carbohydrate?
Carbon. Oxygen.
Carbon, hydrogen,
Oxygen.
and oxygen. Yep. Because they are hydrated carbons, essentially. Okay, most of them are going to be polysaccharides, where they are, as Mike referred to it, made up of monosaccharides. That's the building block. And a monosaccharide is something that can no longer be broken down any further and still be considered a carbohydrate. Okay? It can be broken down into individual elements, or like what our body does with it. What does our body do when it breaks down the monosaccharide? Ultimately, what's the final product? No. 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 The ultimate product.
Water.
Carbon dioxide and water.
Carbon dioxide. Thank you, because it's a carbon, so it can't have water. So yeah, carbon dioxide is the fully oxidized carbon. Okay, I mean, it has 4 bonds to oxygens because there are 2 oxygens, and so it's fully oxidized. So that's the ultimate fate. All right, they do play a role as an energy source, cell-cell interaction, immune recognition. So are they our primary energy source?
Nope.
No. What is our primary energy source?
Lipids.
Fats, right? The lipids. Okay, and so that's why, because they are, well, if it's a saturated fat, it's fully reduced, as reduced as it gets, and so that way you can get as much energy out of that, much more so than you can out of a sugar. Okay, but there is one exception. Does anyone know what's one organ in your body that it utilizes glucose and only glucose? It doesn't have any fat storage. It's your brain. And so actually most of your glucose under normal conditions is going to be used and stored, used, not stored, but used for your brain's function. Okay. And I mean, there's just no way for us to store enough sugar around, carbohydrates around, for that to be our main energy source. Okay? Because what is stored sugar called? Like, how do we store sugar?
Glycogen.
It's glycogen. In us, it's glycogen. All right. And so now it is also used for cell-cell interaction, immune recognition. So for those of you in immunology, I'm sure you probably talked about carbohydrates. So for example, one that we'll talk about towards the end of this chapter is the ABO blood groups, and how the only way that they differ is by, polysaccharide is being expressed on the blood cell. Okay, but in general, they all have this, they typically have this formula of CnH2n, that's why it was a hydrated carbon. And usually for the monosaccharides, they vary from having 3 carbons to 8 carbons. And then we can have either a ketose versus an aldose. Ketose means it's a ketone containing sugar. Ose, by the way, is the ending for sugars. Ace was the ending for enzymes. Ose is the ending for sugars. So ketose means it's a ketone containing sugar. Aldose is an aldehyde containing sugar. So these are the monosaccharides, and they're classified by the number of their carbons. So if it has 3 carbons, what kind of sugar is it going to, what are those sugars called? Triose, so it's a triose. If it's got 4, it becomes, pardon? What's 4? It's tetrose. 5 is pentose and hexose and heptose, right? Okay. So they utilize, in biochemistry, we typically don't say R and S. They utilize the old way of looking at enantiomers, which, just to review, what's an enantiomer? It means it's chiral, but what does that really mean? Well, it's more than a mirror image, because not all mirror images are enantiomers.
Does it have to do with plain polarized light?
It does, but what's another way of thinking about it? For a carbon, it's four unidentical, four different things hanging off of it. It's where the mirror image is non-superimposable upon itself. There's absolutely no plane of symmetry. So that's why your left hand and your right hand, unless your parents or first cousins, your left hand and right hand are considered, would be like enantiomers. Because if you line them up, then your pinkies and your thumbs don't match up. And so, unless I had one student who's like, but mine do. And so, yeah, no. I mean, it's, yeah. So, I think that she was really worried. Oh boy, I gotta talk to mom and dad about this one. So, but it's based off of glyceraldehyde. And so, even if it has 8, and by this point in time, you really should once again remember, be able to have drawn glyceraldehyde, because it's based off of glycerol. And so just to review, we have glycerol has 3 carbons, and so normally this would be glycerol. Of course, whoops, OH, and then each carbon has to make 4 bonds, and so the remaining bonds around each carbon is a hydrogen. So the top and the bottom one has 2 hydrogens, or have 2 hydrogens, and the middle one has 1 hydrogen. But to make it glyceraldehyde from glycerol, you just turn one of the alcohols, one of the terminal alcohols, into an aldehyde. So that's why I didn't want to put the hydrogens in yet. And so now we have glyceraldehyde. Just like if it's glycerate or glyceric acid, but in vivo it's glycerate, you would have turned, instead of turning it into an aldehyde, you would have turned it into carboxylate. Okay, and yeah, that's fine. I'll just leave it at that. And so glyceraldehyde, what they do is they look at the penultimate carbon, which is the middle carbon in glyceraldehyde. What does penultimate mean? And it's a word that doesn't usually get used a lot. No, penultimate means next to last. Okay, and so they look at the penultimate. This is the last carbon. So for glyceraldehyde, it's the second. It's the middle one. And if the alcohol is on the right hand side, it's called D for dextra rotary. Dextra means right. If it's on the left, which this one's not, it's called L for levorotary, for left. But yeah, this would be D-glyceraldehyde, and its mirror image would be the L-glyceraldehyde. And I state this because the fact is, it's really easy, really, really simple. I don't have you guys memorize all of your sugars, except you're going to know glyceraldehyde by the end. I don't have you memorize all of your sugars. I had to memorize all the way up to like 7 or 8. Because well, first of all, it's hard. And secondly, because they're not like organic compounds to where if you just looked at the R versus the S, they look identical except at 1 carbon. These are completely different the way they do sugars. So I don't have you memorize their names. But I do want you to be able to tell if it's D versus L, which is a really simple thing to do. And so that's why if we look here on this one, we have, do that every time. We have a D-glyceraldehyde. Of course, if it's the keto triose, that's D-hap. Well, actually not hap yet. There's no phosphate. So it's a dihydroxyacetone. For those who've already had organic chem, you know that acetone is just the simplest ketone. It's 3 carbons where the middle carbon is the ketone. And so dihydroxy is where it's just like glycerol, except the middle carbon is a ketone. So that's dihydroxyacetone. Okay, but if we look at each of these, we can see, well, they've drawn all of these as being D, but you just look at the penultimate carbon. So for example, this one is the penultimate carbon. And if the alcohol is on the right-hand side, then it's the D sugar. If the alcohol was on the other side, that would have been L-glucose. So that's why it's different than organic chemistry, because normally in organic chemistry, we would have drawn the mirror image of the D-glucose, and we would have called it L-glucose, but that's actually different or sugar altogether in biochemistry and biology. Okay, and then fructose is the keto hexose. So aldotriose. So what they do is they put the number, like the tri part, goes next to the ending for the sugar, and then you state aldo or keto for the whether it's an aldehyde or a ketone. And this is ribose. It's also D. Once again, if we look at the penultimate carbon, it's on the right-hand side. The alcohol is, so D-ribose. And what is it used for? That's in its open configuration, but what is it used for when it's closed? It's RNA. And then 2-deoxy-D-ribose is just where the alcohol has been removed, and of course that, when it's closed, is used for DNA. So this is a Fisher projection, which is a review from Organic Chemistry, Organic Chem 1. So for those of you currently in Organic Chem 1, this is something that we get to actually really soon. I think it's just later this month. But what they do is it's just a way, it's a more simple way of drawing, instead of using these perspective drawings where you have to have the hashtags. You have to have the hash mark versus the wedge. Remember, the wedges are coming out towards you, the hashes are going away from you. What they do is they just draw it as a little cross, and so you don't even put the center, the intersection point is the carbon, and you just need to memorize that the vertical lines are going away and the horizontal lines are coming towards you. Okay, and so that's just called the Fisher. It's just a way of depicting a tetrahedral stereocenter. And so that's the way that they usually will draw sugars. They'll draw it something like this, like what we've been seeing. And of course this, well, it's supposed to be a hydrogen. Boy, next door, they're really working hard, aren't they? So, what kind of sugar is this? The one that I just drew. A pardon? So it's got 5, and so how would we name it? Not the official name, but just the class name. It's an aldopentose, and is it D or L? It's D. So this would be a D aldopentose. So I would expect you, if I said draw an L hexotriose. No, draw in like an L keto hexose or something. I would expect you to be able to do that, but I wouldn't have you name, oh, this is, mannose or whatever it is. I don't even remember now. And so we had to come up with a lot of funny sayings to try to memorize all of the possible sugars. There was like 70 or 72 or something like that we had to know. It's just ridiculous.
So the ketones, if it is larger than 3, are there going to be 2? Like, is there going to be one on each end? Or just one?
No, so I can draw an example. I think I know what you're saying. It would look something like this. CH2OH. I mean, they are really going to town next door. It's like coffee talk. So this would be an example. And I would say, what class, including the stereochemistry, D and L means stereochemistry. What class of, sugars is this, which I haven't counted myself. Okay. So first of all, is it D or L? It's L.
Hexose?
Right, this is an L-keto hexose. Because once again, you're only looking at this in the ketone is always on the lower numbered end. Okay, so if it was directly in the mid, which it's almost always, for those that are biologically relevant at least, it's always on the second carbon. I can't think of a time when it's not on the second carbon. Okay, which actually I've already covered this, the D versus the L monosaccharides. And it's the penultimate carbon, and the reason why it's the penultimate carbon is because that's the last of the chiral carbons. And then it's all based off of glyceraldehyde, once again.
What
So, I mean, it does. It does. And so, I talk about it a little bit later on, but it could be like a nitrogen, then that's an amino sugar. But you could still have a D versus L because it would presumably still have an alcohol on the other end.
So, but then would it still be classified by the OH being on the left or the right? or
Yes,
would
the
it
OH would take priority over the NH2. Sorry. And in theory, you could have like a sulfur or something, but those that you normally see are acetyl groups or amino groups, and they still go according to the alcohol. Assuming that there is an alcohol, it's not some type of deoxy thing. Okay, and so this was just to have an example of, more practicing. So if we look at the top left, what class of sugar is it?
Eight. Wait,
Okay. So it'd be D-aldohexose, and if we look at this bottom right-hand one, what would it be? It's an L-aldohexose. So, and those are the specific names. And so that's one of the reasons why I wanted to, in particular, to point out the bottom two, because it's why, this is D-glucose versus L-glucose, and it's not just because you flip that bottom carbon. It's where you have to flip the entire thing, and so that's why they don't really look at things alike, and so that's why I don't have you memorize all of the possible names, like glucose, fructose, mannose, xylose, fructose. I already said that one, didn't I? What do you get? The galactose, so on and so forth.
It's like AM? Oh, no, I'm right.
Okay, and so we've already talked about enantiomers. That's just stereo the stereoisomers where the mirror images are not superimposable. Diastereomers are stereoisomers that are not mirror images. And so it is possible to have that, and so that's why they're showing this with the 4 aldotetroses, and in particular for those who are currently in organic chemistry, we haven't covered this yet, but for those who've already had it, then we have covered it. And so, but the example here is the fact that we have the two enantiomers of erythros, but if you compared erythros to threose, that's only where one of the alcohols has been switched, not the other. And so that's why these are still stereoisomers of each other, but they are not mirror images. So that's why they're called diastereomers. So you have to have at least 2 chiral carbons in order to have diastereomers. Okay. Of course, if you have more than 2, then you can have multiple diastereomers.
You said they're enantiomers, but not.
But technically they are going to be stereoisomers of each other, but they're not mirror images. Technically, a chiral carbon and an enantiomer would be ones where the mirror images are not superimposable on each other. This is just a little bit, I think that one came from one book, one of them came from a different edition. But it's the same thing, it's just color coded instead of just letters. Now this is the Hayworth, okay, and so typically, especially those that can form 5 or 6, if you remember way back to like chapter 2 or 3 of Organic Chem 1, the most common cyclic or ring structures have how many atoms in them? 5 and 6, and the reason being is because they are really close. Well, 6, if it's cyclohexane, it's a perfect tetrahedral, and so they are very happy being cyclical. And that's the same thing is true with sugars. In vivo, many times, especially if it can form 5 or 6 members in its ring, it does so. Okay, and the ring can flip. It can flip open, closed. So that's why it's really simple. And the reason being is because we have both a good nucleophile and a good electrophile within the same compound. And so if you remember back to organic chemistry, remember I always said that intramolecular reactions are much easier than intermolecular because it's like a scorpion stinging itself. It can just easily attack itself versus trying to find a partner to attack. And the technical term for that, and the reason being, I should state, is that there's an alcohol, and then that's the nucleophile, and then the electrophile would be the carbonyl carbon, whether it's an aldehyde or a ketone, it's still an electrophile. And so it's easy for it to attack and form, if you remember, the term for that tetrahedral intermediate there is called a hemiacetal. Okay. And so the way that they show this many times is it's called a Hayworth projection. And this is the typical way that you are probably used to seeing it. Let me move this out of the way. You know, the way that we draw DNA, for example, or RNA. I'll do RNA because it's what I'm more used to. You know, and so that's where we have it's attacked itself. Let's see. H2OH. And then the alcohol, or the carbon, this was the carbon that got attacked. It's got a special name. I don't want to give it away yet. It's got a special name. And then the resulting alcohol here in the hemiacetal can either be popped up or popped down. And that does matter. And so they have to be able to tell, like, is it up or is it down? And so that's why if they don't know, or if it's like 50-50, sometimes they'll draw it this way. I'll show you what it looks like. Oh, of course it doesn't let me do it, so I'll do it in a different color. Instead of drawing it up and down, they just draw a little squiggly line, which means that it's both. It's either or, I should say. But, okay. All right, and the electron pushing for this is really, really simple. In fact, I think I'll just go ahead and draw it out. This is a review, and for those who are currently in organic chemistry, we don't need to cover this into Organic Chem 2. But what I'm saying, and the easiest way to do it is, let's just draw an example. And we've lost it. Well, I'm just drawing the aldehyde right now for what will be an aldose. It says it's still with Apple TV. There we go. I just drew it out, and I just put all the alcohols on the right-hand side for this time. So we actually already have nucleophiles here and the electrophile that can be attacked. And so if it's this oxygen that does the attacking, it's going to go up and smack that carbon, bang, and this will pop up to form. In organic chemistry, many times we talk about forming a tetrahedral intermediate. Here it actually stays because it's fairly stable, okay? But it's very similar to that. If this is the one that attacks, this is the oxygen that will be part of the ring. So this ring will be 1, 2, 3, 4, 5 carbons. Five members long. So the way to draw that, so once again, the electron pushing would just be this coming around, smacking that carbon, bang. Sound effects optional. And then one of the double bonds has to break. Okay. So the way to know, and it matters, when you draw out this, the way to know if the alcohol is going down or going up does matter. And so what you need to do is just imagine, let me change the color to something completely different. Okay, what you're going to do is rotate the entire compound down. What's that? Negative 90 degrees. It's been a while since I've had that kind of math. But any of the alcohols that's on the right-hand side then will be going down. If it was an alcohol that was on the left-hand side, it would be pointing up. And so this is the oxygen that is here. So this is the carbon that got attacked. So it's right there. So then we just go down the line. These two carbons here would be right there. And so I'm going to go ahead and draw them in. And both the alcohols are going down because they're both on the right-hand side. But we still have this CH2OH because it's hanging off of the same carbon that the nucleophile was on. And so what happens is it becomes like a little tail. I always refer to it as like a scorpion's tail, but it looks like this. There it is, CH2OH. These were all hydrogens. And then the new alcohol, the one that was here, originally part of the carbonyl group, it could either, if the nucleophile attacked it from below, it's going to be on top. If it attacked it from above the plane, it's going to be below the plane. So that's why it could be either up or down. I haven't drawn it in yet. And so let's say that it attacked from below. So now the new, and I'll put it in this color, alcohol will be on the top. And so that's one possible product. The other product is the one was that gold colored would be on the bottom and the hydrogen would be on the top. But we have to be able to tell the difference between these two. And so that's where they talk about alpha versus beta sugars. And so this, when we started off with, what kind of sugar was it? It was D. And how many carbons did it have? Oh, was it an aldose or a ketose? Okay, it's an aldo pentose. Well, this is still technically D. It's just hard to tell that, but and the reason why is because it came from a D. Okay? But now we have to say if it's alpha or if it's beta. If the resulting alcohol, the new alcohol, that's hanging off the carbon that was attacked, if it's on the same side as the scorpion's tail, it's a beta. So that's why this is technically beta. If it's on the opposite side, it's called alpha. Okay, so this is going to be and technically this is going to be a beta D pentofuranose, but we'll get to that in just a moment. Because this one we only had one possible. No, actually we have two. We could have attacked what had been the scorpion's tail, and then it would actually be a 6-membered ring. But I've got examples of that coming up. But once again, beta means it's on the same side as the scorpion's tail. If you started off with the D sugars, which those that are naturally occurring, typically almost all of them are D. If it's on the opposite side, it's an alpha. And so that's what this is trying to show here. And so what they've already done is this is glucose, they've just redrawn it by rotating it down that negative 90 degrees. And by drawing that down this way, you can see which ones are going to be, those that were on the right-hand side will be facing down, those that were on the left-hand side would be hanging up, will be, pointing up. And you know what? The Madonna is not going away. And so, okay. And so if it's a 6-membered ring, it's called a pyranose. And I'll show you the reason why. Because it looks like pyran. If it's a 5-membered ring, it's called a furanose. Because it looks like furan. So that's why, technically, RNA would be a ribofuranose. The D, once again, just came because it was originally from a D sugar, and then the beta versus the alpha. And again, the beta is because it's on the same side as the scorpion's tail, alpha is on the opposite. The carbon that got attacked has a special name. Does anyone from organic chem remember what that name was called? Anomeric. It's the anomeric carbon. Here we go. I mean, it's like, did they die? Before it was like a little coffee claps going on next door, and now it's like, I'm almost thinking we need a don't drink the Kool-Aid kind of thing. It's a Jonestown reference, which is before your time, but not mine. This is faith integration of sort. It has absolutely nothing to do with biochemistry, but I'm sure I could relate it to it somehow. Jim Jones is the one who did he was the minister, that did the Jonestown massacre, and which is the largest, to my knowledge, at least the largest of the Western cults that had mass suicide. He was originally from Indianapolis, which is where my mom's from, and so my mom had actually gone to the same church that he did before, because he used to be, at one point in time before he went really crazy, he was Pentecostal. Yeah. And so then he went kind of nuts and then moved to San Francisco and became really nuts, and then ultimately moved them down to Jonestown, Guyana, where they murdered the congressman and then killed themselves. Oh, almost 1,000. I think it's like 900, 800 or 900, including little kids and those who didn't take of the Kool-Aid and were shot. And so, yeah, very few survivors.
I think that they were like gonna go to heaven if they drank the
Yeah, some of them did. Yeah. Yep, they were crazy. And so, I mean, we could talk about the metabolic pathways involved, but it was cyanide, and so I think that if I remember right, it's cyanide. Of course, when I was a kid, it happened whenever I was a kid, so I wasn't thinking, oh, wow.
Don't drink the Kool-Aid.
Don't drink the Kool-Aid. So that's my word of advice to you all. Okay.
Moving on.
Anyway. No, we don't want to go there. That's axial versus equatorial. And so this is the whole reason why they were called furanoses, and furanoses is because they look like furan and pyran. And that's like the extent of what I want you to know from this. And so to recognize if it's a 5-membered ring, we usually draw it where the oxygen is on the top, then it's a furanose. If it's a 6-membered ring, and usually whenever we draw that, you've seen it, the oxygen's on the top right-hand side. That's just a typical way. And of course, then we have to have things hanging off. Well, it's supposed to be attached, but you get the idea. Then those are called pyranoses. So the glucopyranose is the one that you've seen probably stereotypically seen the most, because that's the one that's used to make glycogen. Whereas the ribofuranose is the one that's used to make RNA and DNA. And so, boy, he actually got a couple steps in before he realized his class hasn't started yet. Okay, so even though we still have like 3 or 4 minutes, I'm going to go ahead and